Okay, welcome back, AP Calc people. Hopefully the AP exam went well. We're going to cover a new topic, and for seniors, last topic of a super important application of integration. So we won't just be like finding integrals for just the sake of doing it. We're going to actually know why somebody actually cares so much about the area between the curve and the x-axis. So let's look at a sort of simple, basic example and then just up the ante, basically, of that sort of concept a little bit more with just more complicated functions each time. So we'll start with this. You've got a velocity function. This is your velocity function, time. So velocity function just sitting there. We want to find the distance you cover in 4 hours, assuming this is your velocity. Well, this is a pretty simple velocity. It's 60 the whole time. The velocity is just constantly 60. It's never changing. So if we go 60 miles an hour for 4 consecutive hours, 4 hours at 60 miles an hour should get you 240 miles. Part A, done. Really just not that bad. Whereas part B asks you, like, what is the area between this graph and the x-axis? That is a big giant rectangle. And that rectangle is 4 wide and 60 tall, so 4 times 60 is 240. So once again, we're getting back the same answer, which we should, because you kind of know that integrals, or that integrals are involved in this, or should be, because you know the FTC and you know the integral gets you area, and you also kind of know that the antiderivative of velocity is position, so we should be able to get some values back here. So let's look at this concept again in a slightly more complicated function, just slightly, and talk about how that works and the subtle little different things you can be asked here. So you're given a graph this time of some 1, 2, 3, 4. Of some v of t function that equals -1/2 t plus 4. And we're asked a couple things about this function this time, which is, what is your displacement, aka change in position, from t equals 0 to t equals 10? So essentially what we're saying is you could integrate this velocity function from 0 to 10 to answer that question. Which kind of makes sense, just even without even thinking too deeply about the FTC, because you know the derivative of position is velocity, so the antiderivative of velocity should take you back to position. The way the FTC works is you find that antiderivative, you plug in that number, you plug in that number, and you're going to subtract them. Well, when you're subtracting, you're calculating change. So all you have to do to get the change in position, which is sort of called displacement, is just find the antiderivative, plug in top number, plug in bottom number, subtract, done. So let's just do that. It might help you to rewrite it as -1/2 t plus 4 in here, and then we'll just like do it. You're going to bump that t up to t squared, but you're going to need a quarter in front instead of a half, because the 2 comes down, double the quarter, you get a half, plus 4t. We're going to plug in 10, and we're going to plug in 0, and we're going to subtract them. So we get -1/4 of 10 squared, plus 4 times 10, minus -1/4 of 0 squared, plus 4 times 0. And that's going to be useless on the end because we're just plugging in a bunch of zeros, and that's just going to get me 0. So this should be -1/4 of 100, so that's -25, plus 4 times 10, that's 40. We don't even really have to do that calculation. Should get 15. And that should be in miles. And then everything's kind of good. So ultimately, we're good there. You might have thought, it might have been easier to do it in a different way. Since these are just making shapes, you could have just found the area of these two triangles and just as a way to do the integral rather than finding the antiderivative. So this triangle is 4 by 8, so half of 4 times 8. And this triangle, which is actually kind of upside down, is 2 by 1. So you can either just subtract these values or just think of this 1 as being negative. It doesn't matter. So minus half of 2 times 1 should get you half of 32, that's 16, half of 2 is 1. Yay, 15. We get back the same answer. So everything's pretty much good here. So, I don't know. This is fine. We got the change in position, and the change of position is 15. So, part B almost feels like it's asking you the same question, but it's asking you something subtly different. And here's this subtle, let me sort of just dig into the subtle little difference. It wants the distance traveled. So, here's our derivative. It's right there. That's the graph of velocity. And velocity is positive before 8 and negative after 8. So that means you're going to the right, and then you're going to the left. So what we really just calculated before is we started somewhere, and we really don't know where, and we ended 15 units away from where we started. But now we know that we're going right and then left, and yeah, what we calculated was this was 15, that at our t equals 0, and that's our t equals 10, that was 15. That doesn't mean we went 15 units, because we went past that spot we ended at and then doubled back, so we covered some additional distance there. So the issue is, like, the velocity being negative means we're backtracking over ground we've already covered, so our change in position and our distance traveled is not the same thing. Unlike the first example where the velocity was always positive, so the distance and the displacement are actually the same thing. Here, the distance and displacement are going to be different things because we're backtracking over ground we've already covered. So what you kind of want to do here is integrate from 0 to 8 the v of t function and figure out how far you went to the right before you turned around, and then add back the v of t function you covered from 8 to 10 for the distance you covered left. But the problem is, you can kind of see it on the graph, is the distance we covered going left is going to be negative based on how the integral is kind of defined to work. So you will need to, like, turn this negative stuff positive yourself, and you can either do that by putting a negative here, or instead of adding, which is how most people prefer to do this, just subtract the stuff you know is going to be negative. So let's just do this the kind of easier way. That triangle, that green one, had an area, because we did it before, of 16. And this triangle has an area of 1, but it's negative, so it's down, so we're actually going to be doing minus negative 1, because this little guy is upside down. You should wind up getting 17 here. So this one's a little different because the velocity is negative at some point in time and you backtrack. So distance and displacement are not actually the same thing. So the big takeaway, hopefully, from page 1 is that if you integrate velocity, you're going to get back displacement. But if you integrate the absolute value of velocity, where we turn the negative stuff positive, which is kind of what we're doing here, you're going to get back you're going to get back distance traveled. So what you kind of want to do is basically flip all this stuff up so that we get everything positive. So there's a really, really easy way to turn this stuff positive without you having to worry about figuring out when it's negative and figuring out when it's positive. So you could just integrate from 0 to 10 the absolute value of velocity, and that'll turn everything positive, because with distance we don't care which direction you're going. So it's almost like you're integrating speed to get back to get back distance. And speed and velocity are closely related, as are displacement and distance are closely related, but not exactly the same thing. So slightly different going forward, now slightly actually different going backwards as well. So we're going to talk about how to do this more efficiently and for more complicated functions soon. But the big takeaways are that if you integrate velocity, you just get back displacement, and when you integrate the absolute value of velocity, where you turn everything positive, you get back distance. End of page 1.